So the last thing that we need to be able to do in chapter 4 is to be able to write an electronic configuration. Unfortunately, the textbook does not show you how to do that, and you need to know how. And so I'm going to show you how to do it. Now, an electronic configuration looks like this. I'm going to show you one. You have carbon, and it looks like this. It's like 1s2, 2s2, 2p2. This is what the electronic configuration for carbon looks like. And like I said last time, we have these things called primary quantum numbers. And that's what those are. All right. And so these correspond to the levels that we had the other day. Okay. And then we have our sublevels, and that's what these guys are here. These are sublevels. And as I said before, we have S, P, D, F, F as our sublevels. And the big difference that we see are these guys right here. This is the number of electrons in the sublevel. Okay? So within a sublevel, you have electrons and orbitals. And within a n level, you have sublevels. And so we have S's and P's, and we have S's, P's, and D's, and so forth. All right, we won't worry too much about F's for our purposes. But we do have S, P's, D's, and F's. So we need to be able to come up with what's called the electronic configuration. And for carbon, it's 1s2, 2s2, 2p2. And by the way, these numbers that are superscripts, they just refer to the number of electrons. It's not a mathematical, like to the second power or anything like that. Okay, so how are we going to do this? So what we do is we look at the periodic table and we divide it up into S, P's, and D's. And it turns out the reason why the periodic table is the way it is that it is actually because of the way the electrons are arranged. So for instance, this block right here is the S block. And this block right here is the P block. And everything in the middle over here with the transition elements is actually the D block. And so we have S, P, and D level elements. And while we will not be doing F level blocks, the actinides and the lanthanides, these are all F level blocks. And it turns out that the periodic table is actually arranged according to the electronic configuration of the elements. It actually turns out that because of the way the electrons are arranged in the elements, this is how they react, and they end up having these periodic properties, and we end up with families. So we have the S, P, and D blocks. And it turns out, if you look, the S block is 2 wide, and the P block is 6 wide, and the D block has 10 elements. And so this actually fits very well with what we discussed before, which was S sublevels have one P, pardon me, S sublevels have one S orbital, and every orbital has 2 electrons. And so if you have one orbital, you have 2 electrons. And P sublevels have 3 P orbitals, and each orbital has 2 electrons. Well, if you have 3 orbitals and 2 electrons apiece, well, 2 times 6 is 6. 2 times 3 is 6 electrons. And look there, you have your P elements is 6 across, corresponding to 6 electrons, 3 P orbitals. And the same thing with the D. The D elements, well, there's 5 D orbitals and 2 electrons apiece. Well, that's 10 electrons. And look at that. You have the D level, D sublevel, and it's 10 elements across. And same thing with F. You have 7 orbitals, 2 electrons apiece, 14 elements, 14 electrons. And so actually it turns out quite nicely that the periodic table is arranged in accordance with the number of electrons in each sublevel. So what we're going to do is we're going to go left to right, top to bottom, as we try to write out our electronic configuration. Now look, the S and P elements, which is the only ones we're going to focus on. We're not going to do the D elements. We're just going to do the first 3 periods. The S and P elements are going to be the same as the period. Okay? So it's going to be the same as the period. So what we're going to do is we're going to start with hydrogen. Hydrogen is row 1, period 1, element 1. So for hydrogen, we would say it's on row 1 or period 1. That gives us n equals 1. It's an S element, so we say 1s, and it has 1 electron, 1s1. So hydrogen is 1s1. Now for helium, we jump across. Now, for purposes of doing this, helium is going to be an S element. Go ahead and erase some of this. Okay, for purposes of helium, we're actually going to put helium right here as an S element. We're not going to have it over here. I know it's over there in the noble gases, but it's actually an S element. So for helium, we would say it's in row 1. There it is. It's an S element. And we go 1, 2, 2 electrons, and it's 1s2. So that completes the first row. Let's go ahead and mark this off. Now remember, what we're doing is we're always starting with hydrogen. We work our way from left to right, top to bottom, and we always start with hydrogen. So if we look at lithium, which is on row 2, we still have to start with row 1, and we go 1, that's row 1. It's also the N number, primary quantum number. And we say 1s, and there's 2 electrons on the first row between hydrogen and helium. Then we drop down to the second row and we say 2, and lithium is still in the S block, and there's 1 electron. So we say 1s2, 2s1 for lithium. Now, we can go on to beryllium. I'll go ahead and erase this. Let's go on to beryllium. Be. And we put it in square brackets. And once again, we have to start with hydrogen. And we go left to right, top to bottom. And we say 1s2 for the first row. And then we look down and we see lithium. We have to work left to right. We say it's on the second row. And we say 2s. And then we say beryllium. Let's see, that's 1s, 1s2. There's 2 electrons in the S sublevel for beryllium. As we go across, lithium is 2s1, and then beryllium is 2s2. All right, so let's jump across to, not going necessarily in order here, let's jump across to carbon. We look at carbon. Carbon's over there, it's the 6th element, but we still have to start with hydrogen. We go left to right, top to bottom, and we look at the first row, and we have 1s2 because we filled up the S block. And then we jump across, and we have to start with lithium, and we look at lithium, we say 2s for lithium, 2s1, 2s2, that fills up the S block. And then we jump across carbon, and we see boron, and that is still on the second row, but now we're in what? We're in the P block. And so since we're in the P block, we start all over again. Boron would be 1P, 2P1, and then carbon is 2P2. You got to understand, it's the number of electrons that are in the particular block. It's not the total electrons, it's the particular block. And a matter of fact, if you look at this, you say, well, we have 2 electrons in the 1s2, we have 2 electrons in the 2s2, and we have 2 electrons in the 2p2, and that gives me 6 total. And if you look at carbon, what do you have here? It's element number 6, and of course we know that if you're element number 6, that means you have 6 protons, you also have 6 electrons, and sure enough, the electronic configuration has 6 electrons. All right, well, let's look at one of my favorite elements, which is chlorine. Let's take a look at chlorine. And chlorine is down on the 3rd period. And so we still have to start with hydrogen, and we go hydrogen, helium, and that's the first row, and so that's 1s2. And then we look at the second row, and we have to start on the left with lithium, and we say, well, lithium, let's see, that's S, that's 2s, and then we go to beryllium, that's 2s2, and then we go over to boron, and then we're in the P block, and we go 1, 2, 3, 4, 5, 6, and we go 2p6. And remember, we're heading to chlorine, and we're dropping down to the 3rd row, and we say 3s, and we look at sodium, that's 3s1, magnesium's 3s2, so we say 3s2, and then we drop across to the 3p, and we go 1, 2, 3, 4, 5 with chlorine, and we say 3p5, and there it is. Okay, so if you look at the periodic table, it's arranged in terms of S's and P's and D's. Now, we won't mess with D's because, well, this is not what we're going to do in chemistry 130. But, look, I mean, it's literally you start with hydrogen, you work your way left to right, top to bottom. So that's how you do um, electronic configurations. Okay, we need to be able to do that for quizzes, homeworks, and tests. All right, now the final thing that I want to talk about today to finish up the chapter is periodic properties, and that's what we're going to do. Assuming it's going to let me pull it up here. Wait a minute, here we go. It's periodic properties. And there's really only two periodic properties that we're concerned about, although there are several that occur. And the first one we want to do is size. And the way it works is contrary to what you might think. As we go left to right, we get smaller. Atoms actually get smaller as we go left to right. Even though there's more stuff, they actually get smaller. And as we go top to bottom, they get larger. And this is because of the increased number of protons attracting the electrons in as you go left to right. But as we go top to bottom, we are completing shells. And that's how it goes as far as the size. We go left to right, we get smaller. As we go top to bottom, we get larger. And the last thing that I want to mention is something called electronegativity. And that's how much the atoms really want electrons. And it turns out that fluorine is the most electronegative. So if we go electronegativity, fluorine is the most electronegative. And these guys are not electronegative at all, the noble gases. And as you go away from fluorine, these are actually less electronegative. And what this has to do with is just how bad do the elements want electrons? And fluorine really wants electrons. The noble gases don't want electrons. And as you get over here towards the left, they really, really, really don't want electrons. Particularly the alkali metals, they don't want electrons so much that they actually give them up and they become positively charged. And the elements towards the right-hand side of the chart actually become negative when they become ions. And so that's your periodic trend that you're looking at, is how bad do they want the electrons? And it turns out that fluorine is the most electronegative. So anything that's not fluorine is going to be less electronegative.